Turns out you have different notes than I do, and I wrote the notes. I cannot explain how that happened. Here we go. The finale, the last one, special K. Okay, this is the solubility equilibrium. This involves the dissolving of a solute in a solvent. You know those three types of solutions. Unsaturated, saturated, and supersaturated. Turns out that the reason we call them all of these things has to do with the solubility equilibrium. Okay, take a wild guess at equilibrium what type of solution you have. Saturated is correct. Good job. Okay, the solubility product constant, KSP, indicates how soluble a solid is in water. If KSP is very small, that means it's not very soluble. Let's just take something, silver chloride. If it dissolves, breaks into its ion. If the KSP is very small, that means that equilibrium lies to the left, which would mean that it doesn't dissolve. If equilibrium is very large, that means it lies to the right, that means it does dissolve. Very small is I'm not fooling around small, like KSP values that are times 10 to the negative 30 something, times 10 to the negative 70 something. That's pretty itsy.
So what's large?
Itsy. You know what? Somebody, not now, but somebody needs to look up the KSP for sodium chloride. It may have a KSP that's so large it's not even published because it's totally soluble. Okay. So KSP equilibrium would be something like this. Even though substances are considered insoluble, they will dissociate to a small extent. So the KSP equation, or I'm sorry, the KSP expression would be just the ions. So the KSP for silver chloride would be this. We would leave out the solid silver chloride since we never put solids in an equilibrium expression. So the exponents are the coefficients of the ions. Leave the solids out. Okay, let us write the KSP expression for the following. Oh, well, you give me two really easy examples, then I'm supposed to do this on my own on a Monday? Why, yes, you are. So I will do one for you. Calcium phosphate will dissolve into its ions in this manner. It will produce 3 calcium plus 2 ions and 2 phosphate ions. So KSP then, for this particular, will be the calcium ion raised to the 3rd power times the phosphate ion raised to the 2nd power. Good? Potassium chromate dissolves into 2 silver ions and 1 chromate ion. Turns out I'm doing both of these for you because I'm filming and don't want to stop. So KSP is equal to the silver ion raised to the 2nd power and the chromium ion raised to the 1st power. Okay. Calcium phosphide is added to water at 25 degrees C until equilibrium is established. That would be this. If at equilibrium the calcium plus 2 ion is 3.42 times 10 to the negative 7th molar, what is the KSP for calcium phosphide? That's frightening. I wish the door would close. Somebody who's braver than me, go close the door. Okay. Alrighty, so we have our KSP expression. We have the, thank you. we have the equilibrium reaction that's going to take care of this. Let's do a rice table. Oh, don't you do that. I love rice tables myself.
Isn't it CA3PO42?
Oh yeah, I just got carried away. All right, so initially you have some concentration of the solid. Do we care? No, because it's not the equilibrium expression. We have none of this and none of this. This is why I taught this last, because these rice tables get a little more complex. The change, according to our equation, says that for every 1x of this that dissolves, we will have 3x of this formed and 2x of this formed. Yes? Correctamundo. So at equilibrium, this is what we have. Okay. Now they told us what x is. Actually, they told us what this is. It is 3.42 times 10 to the negative 7. Everybody with me? Okay. So I will do that. 3x is equal to 3.42 times 10 to the negative 7. X is equal to, thank you for those people who are click-clacking away, 1.14 times 10 to the negative 7. Why do I even need that?
So you can find PO4.
So I can find PO4. So I know that the calcium is 3.42 times 10 to the negative 7, and the PO4 is equal to 2x, so that's 2 times 1.14 times 10 to the negative 7, which is equal to I probably could have done that right in my head, 2.28 times 10 to the negative 7. Yeah. So now I am finally ready to put this into the KSP equation. KSP, I decided way up here, was the calcium, 3.42 times 10 to the negative 7, raised to the third power, times my phosphate concentration, 2.28 times 10 to the negative 7th, raised to the second power. I'm so glad I have a calculator, because this ends up to be itsy bitsy. 2.0 times 10 to the negative 33rd. So what that's saying is if you put a lump of calcium phosphate into water, even if you stir it and everything else, you make it into chunks, does that affect the equilibrium? No, it gets it to equilibrium faster, but it does not affect equilibrium. How much of it eventually dissolves. And that, according to this KSP, is not a whole lot.
So
Okay.
For this one, you pretty much just did stoichiometry.
I pretty much, all of this is actually pretty much stoichiometry. The nice part of this is the stoichiometry is set in a regimented way that you already know, which is the rice table. So what we're doing is, a lot of people teach this KSP first. I like to wait until last, because you can write a K value with your eyes closed. You can put a rice table with your eyes closed. You can put these two together with one eye open. And don't tempt me today. People in the first period were like heads down and everything else. Really? Don't be irritating me. Okay, I think just like in Chem 1, solution. The problem with solutions and chemistry is the vocabulary. First of all, everything unhealthily starts with an S. And there's all of these terms, and it's so easy to get them mixed up. In Chem 2, same problem. We got all this S stuff floating around, and it's hard to keep it straight. All right. A saturated solution is a solution that is at equilibrium. And so that means, like if we looked at this, recall this is the solid. If we looked at this particular equilibrium expression, the beaker contains the solid and the ions. All right, got that part. So that is at equilibrium. Something is considered to be a saturated solution. Okay, solubility is a concentration, and solubility can be talked about in two types of concentration. The first one is the one I don't like very much, called grams of solute per liter of solution. We don't use it a lot, but they make us know it. The second one I'm very familiar with, the molar solubility, the moles of solute dissolved per liter of solution. I know that concentration to be molarity. Okay. Now, the molar solubility of a compound, the molar solubility of this, also gives rise to the concentration, the molar concentration of its ions, which would be this. So the molar concentration of the ions, you have to be able to calculate as well. So you have to look at a compound and figure out how many ions it dissociates to. And you have to be able to figure out, let's say if I have 1 molar calcium phosphate, I know I will have 3 molar calcium ions and 2 molar phosphate ions, yes?
Yes.
Okay, you have to be able to do that. Now, the solubility product, look, these terms are pretty much all the same, but different. The solubility product constant is KSP. That's an equilibrium constant between the ionic solid and its ions. This changes only with I will just wait for this.
Temperature.
Thank you. Temperature only. These are all equilibrium positions. Alrighty, so here is my scheme of things. I need to be able to go back and forth between all of these different terms. So if somebody gives me the solubility of a compound unhealthily in grams per liter, I'm going to change it to the molar solubility of the compound. Then I need to know the molar solubility of the ions in order to calculate KSP. If somebody gives me KSP, I have to go this way, or maybe I go this, or this. Got it? You think you do. Here we go. The KSP for silver chromate is 1.12 times 10 to the negative 12. What is the molar solubility of silver chromate? Where on this scheme are we?
Yes.
What is, okay, we are here, and what is the first question they ask us?
Just like molar solubility.
And then after that, we have to, that solubility. Okay, I wish I had left more room, but I didn't. So I'm going to write a couple things in anticipation of actually answering the question. The first thing I'm going to do is write the equation that would be appropriate for this equilibrium. Calcium chromate, which is a solid, will be in some sort of equilibrium with its ions. And the KSP expression that would cover this would be KSP is equal to the silver ion raised to the second power times the chromate ion. Everyone happy? Okay. And I know that KSP is given to me. So I have KSP. I need to find this. So I need a Rice table. Silver chromate dissociates into 2 silvers, 1 chromate. So initially, I have some amount of silver chromate that really doesn't matter, but I have no silver ion and no chromate ion. the change at equilibrium is some of this will dissolve, making 2 times this, and the same amount of chromate. So at equilibrium, I have this and this. Oops, and he's sliding. I think I'm going to have to make my toilet. All right, so how do we figure this out? Plug it into this. Okay, so 1.12 times 10 to the negative 12 is equal to 2x squared. You just, except you're wrong. Watch for a second. Times x. You are wrong. And this is the most common mistake here. Let's do a little algebra. 2x squared is 4x squared. There you go. Times x. Leave him alone. He's really smart. Is 4x cubed. So my first plan of attack, because I am a little challenged in the math department, is I'm going to divide both by 4, and then my x cubed is going to be equal to 3 times 10 to the negative 13. And then I'm going to take the cube root of everything and say thank you to the people who make these calculators, because that is a very easy x. And x is equal to 6.54 times 10 to the negative 5. What is that value?
That is the concentration of zero.
That is the molar solubility of the in moles per liter.
Yeah.
That is the molar solubility. It's X right here. Look, it's X. Aha.
If we wanted to find the molar concentration of the ions, we just plugged it back.
If you wanted to find, yes, just like we did in the previous problem, if you wanted to find the equilibrium concentration of the silver ion, you would take this X and substitute in right here. Right, X is the molar solubility of the silver chromate.
And what's the molar concentration if that's the molar solubility?
What?
What's the molar concentration?
That's the ions.
For the molar concentration of the ions?
Oh, so
We don't need it. We could find that. We just skipped from here to here.
Oh, okay, so
Okay.
molar concentration.
Just plug in the X behind the molar concentration of ions.
So this is the answer to A. What's the molar solubility of silver chromate? Got it. Now, B is what's the solubility in grams per liter of silver chromate. Well, I do recall that molarity is the same thing as moles per liter, so I can do just a little stoichiometry problem right now while I'm waiting. Okay, so if I have 6.5 times 10 to the negative 5th moles per 1 liter, how many grams is that? Well, I'm going to use the molar mass of silver chromate, which tells me that 1 mole of silver chromate is equal to 332 grams.
Did you just do that in your head?
Yes, I did just do it in my
No,
head.
it's on.
No, I did it in my head.
It's right there.
I did it in my head.
She did it in her head last period and wrote it down on the paper.
Actually, I did it in my head while you people were walking in. Okay, there we go. There's the answer. Okay, I did have a kid 2 years ago that thought I was doing it all in my head. Every single problem we've ever done, he was like, I cannot believe you can do that math in your head. And I'm thinking, you go ahead and believe that, my friend.
So that's what you should do.
Come to that kid, you know, making test.
I did just fine. Just fine. Okay, calculate the KSP value for bismuth sulfide Bi2S3, which has a solubility of 1 times 10 to the negative 15th moles per liter at 25 degrees C. Let's look at our little thing. We're going from here. This is where we would like to end up, please.
So
So essentially molar solubility is just X.
Mhm.
I still don't get the difference, because you said plug in that to X, but that is X,
That is X.
so.
I think what you were getting confused is somebody asked me what this was.
I'm wondering what the,
The molar concentration
Yeah,
of the
that-
ions.
yeah.
Okay,
That's-
it would be, according to my Rice table, 2X.
You say you're going from chromate to silver?
Okay, here, this will help you. If I had 1 molar silver chromate, how many molar silver ions would I have?
2.
And how many molar chromate?
1.
Okay, so if I have 6.5 times 10 to the negative fifth silver chromate, I will have, get the, times 2 times 6.5 times 10 to the negative fifth.
You plug in,
That's
so you plug in
what you get for the solubility, right?
Mhm. Are these words already, see, it's all a word game. Okay, calculate KSP for, oh, I already read that. So I'm going to write down my equation, Bi2S3, which is a solid, is in equilibrium with its ions, 2Bi plus 3 sulfide ions. My KSP expression, KSP, would just be based on these ions, Bi plus 3 raised to the second power times the sulfide ion raised to the third power. Everybody with me so far?
yes.
Okay. We could do a Rice table.
Going on.
We can. Here we go. Let's do one. I, C, and E. Okay, so here we go. The change that will occur is this will go down while this goes up in this fashion. Yes? And they tell us at equilibrium that we have 1.1 times 10 to the negative 15th molar. Okay, so far so good? So this is 2x and this is 3x. So in order for us to find KSP, we need to find the equilibrium concentrations of these two things. So for the bismuth, it's 2 times x is this. Oops. And for the sulfide, it's 3. Okay, now I've gone from the molar solubility of bismuth sulfide to the the ion concentration. So I can put it into my KSP expression. And this raised to the second power times this raised to the third power is going to give us this eensy-beensy number. Okay? Remember how on some tests that you took some K, that you were told, or you were asked to rank the strength of acids based on Ka? How'd you do that?
Lower the Ka, the stronger the acid.
Higher the Ka,
You can make that right.
the stronger the acid. The stronger, that told you how it dissociated, how much it dissociated. You can rank solubility using KSP as well. However, there's one really important thing you have to keep in mind. Because of the way this works, you have to make sure when you're comparing solubility, all of the things you're comparing, put the same number of ions into the solution. So silver iodide breaks down into 2 ions. Copper iodide does as well. and so does calcium sulfate, just 2 ions for each one of these. So, given these KSPs, it is not difficult for you to determine then that this is the highest number, therefore it is the most soluble, then this one, and then this one. If we were to have something like the bismuth sulfide that breaks down into a number of ions, you could not use that. You'd have to figure out the solubility using a rice table. Okay, now that was easy. There are some factors that affect solubility. The first one that we're going to talk about is the common ion effect. You remember common ion? That's an ion that interferes, according to Le Chatelier's principle, with whatever you're looking at. So we have calcium fluoride that breaks apart or dissolves into 1 calcium ion and 2 fluoride ions. If we did something nasty and add sodium fluoride, which gives us a sodium ion and a fluorine ion, this fluorine ion will push the equilibrium to the left, meaning more or less would dissolve. Less. Okay, how much less? Well, let's figure that out. Calculate the solubility of solid CaF2 in a 0.025 molar sodium fluoride solution. All right, I already wrote my equation. My KSP will be the calcium ion times the fluorine ion raised to the 2nd power. I would have this. All right. So initially, I have none of this. The change at equilibrium is this goes down, this goes up, and this goes up like that. Oops, I have some of this on mine like a dog. There we go. Got it? All right. So at equilibrium, I will have some value of this gone. I will have some of this present, and I will have the amount that I started with plus 2x. My next step would be to put this into this expression. My KSP is 4 times 10 to the negative 11. So far in your K work, what did you do when you had a very small K?
Got rid of the X.
Got rid of the X. Okay. I did. Sounds good. So I have X times 0.025. Wait. X is equal to here while I'm doing this in my head. So the molar or the solubility of the calcium fluoride is X. Got it?
So wait,
Hey,
it says solubility, how do we know what that
You know what
means?
the solubility?
Doesn't that mean grams per liter? I forgot, I thought molar, so.
that's the stinky part of this. I'm going to specifically ask you for the solubility in grams per liter or the solubility in moles per liter. And the AP exam will do the same for you. I got this problem out of the book that it's not as nice. Okay, pH can affect the solubility. Magnesium hydroxide has what type of salt? Basic.
Basic.
All right, let's say you added some hydrogen ions to this. What would those hydrogen ions do? Yep, they would make water. And the water would be essentially taking this out of the equilibrium, So equilibrium would shift to the
Right.
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 Faked you out. Right, to try to replace the hydroxide ions. So would this be more soluble or less soluble?
More.
More. Okay. Now, in this one, if you added a hydrogen ion,
Do nothing.
it would react with the F to form hydrogen fluoride, which does not dissociate. So once again, we would shift to the right. Okay, now let's just look at these and see how they dissociate. This one will be essentially the same as this, correct? Okay. This one all right, and then the barium sulfate. Why did I do so many of these? All right, which of the following substance will be more soluble in an acidic solution than in a basic solution? Okay, if you add an acidic a proton here, it's going to react with the water, forcing equilibrium to the right. So this would be the correct answer. If you added a base to this, it's going to shift to the left. Calcium carbonate. If you added an acid, a proton to this, what would happen? It would form with the carbonate, making that, which is a, it is not, it's a weak acid. Will it dissociate? No, so it's taking this out of play, so equilibrium will shift to the, what happens if you add a hydroxide?
Forms the CaOH.
You probably have a CaOH too, which has limited solubility, and so I
But
think
isn't it a strong base?
yeah,
Yeah.
we could. It's a semi-strong base. It's semi-strong, so it would probably not have a great effect as the proton would, because this isn't going to dissociate at all. Barium hydroxide is of limited solubility, very limited, and the HSO4 that you would form is limited. So I'm going to say this is a push. I don't think it is more in acidic than in basic. This would be AgOH, soluble or insoluble?
Inside.
Insoluble, so that would make this, in a basic solution, it would be more soluble, yes?
Yeah.
What would happen here?
HCl.
HCl, which would dissociate into?
H.
Okay, so this would actually be more soluble in basic than in acidic. So these are the two correct
That's the
answers.
one we get C.
C? Okay, okay, so we would have the solubility of that, which is, or how this would dissociate to form hydrogen ions, weakly dissociates. And barium hydroxide has equilibrium that lies pretty far to the left. So it won't dissociate, putting OHs out for POH.
So we're just supposed to know that.
Yes, you are actually.
It's because it's a group 2.
Yeah. Yeah. All right. Now, you need to predict whether or not a precipitate is going to form. You need to predict that using Q. Do you recall what Q is?
Yes.
The reaction quotient? That is just like K, only the concentrations are not at equilibrium probably. You know, a lot of times these are the original concentrations that I give you. If Q is less than KSP, let's look at this. So if we have Q is less than KSP, it will shift to the right to form more products. That means that it will dissolve. Something that can dissolve more means that it's unsaturated. If Q is the opposite way, bigger than K, that means that the reaction will shift this way to make more of the solid. That means that it will precipitate. It will make a precipitate. If Q is equal to K, then that means it is a saturated solution. It is at equilibrium. And I'm kind of sad that I made this problem so hard for this original one, but we'll get over it. And so I'm paying you back by making you not do exercise 17, okay?
Thank you.
You're so welcome. A solution is prepared by adding 750 mLs of 4 times 10 to the third molar. I don't even know what this is. I think it's cerium.
I even think it's easier.
Somebody, no, it's not cesium, that I know. Somebody look on
It's-
is it
it's on the
cerium?
left, yeah.
Cerium nitrate to 300 milliliters. Have we stopped and just tried to find, there it is.
Yeah.
It's at the
Number
bottom.
58.
58 bottom left.
It's cerium?
Yeah.
Okay. All right.
Okay.
Bonus points for me. So to 300 milliliters of 2 times 10 to the negative second molar, I can pronounce that, potassium iodide. Will cerium iodate precipitate from the solution? Where did that come from? I don't even know what you people are talking about. Oh, it's a double replacement reaction. Yeah, really? Come on. Let's start with the balanced equation. It's Monday. You're trying real hard to stay awake because I told you I'd be really not friendly if you didn't.
Basically.
Basically, that's the only thing keeping you awake. They even tell you what the product is and the correct formula for it. So we want to know,
So nice.
will this precipitate? You know this is soluble. I will even balance for you since it's Monday.
You're another 3 instead of 5. Serious.
What?
Yeah, you did C.
Oh, I did.
Okay, just making sure I'm doing this.
No. Okay. It's also Monday for me as well. But that is no excuse. I'm supposed to be professional.
Let's see.
And that's not 3, is it the end of iodate? Yeah, it's not 3.
Yeah, it
3.
is. Yeah, it is.
I think these are from.
Right there. Okay.
Moving on.
All right, moving on. I'm only allowed one mistake per equation. Okay. So how do you do this?
Just
I would take a giant context glue from this right here. You have to find Q and then relate it to KSP. Okay, how do I find Q? Q of what? This, because this is what we're trying to find if it's soluble or not. Q is equal to the cerium. Yeah, I heard that enormous sigh over there. This is Q. Don't make me make you do 17. I had to look up the answer myself. All right, how do I know what these are?
It's given to you.
No, it's not.
Hold on.
How do I know?
You find the concentration.
Right there.
Yeah, you can't even do that. You're going to use the number of moles of anything is equal to the molarity times the liter. Oh, okay, I got it, because the cerium that's in here came from here, right? So all the moles of cerium here show up right there. All the moles of the iodine from here show up right here. So if I know the moles of this and the moles of this, I can put it, oh no, I can't. Then I'll have to find the molarity, okay. So one step at a time. So the moles of cerium that are in here are equal to 4 times 10 to the negative third times 0.750. And the iodate moles are equal to 2 times 10 to the negative second times 0.3. And so this is equal to,
These numbers.
3.75 times 10 to the negative third moles. And this is equal to 5.7. Why is it equal to 6? Something. Yeah, yeah, 0.006. Is this right? No,
It's
this is 3. Okay, I went right to the molarity, sorry. Moles.
Say
When I was doing it in
3/4.
my head, I skipped a step. So that's how many moles we have, and in order to put it in a Q, we need to know the molarity. So if this is the number of moles, I need to know the total amount of solution. The total amount of solution is 1.05 liters. So the molarity then is equal to, now can I use 3.75 times 10 to the negative third?
Sure.
Okay, and 5.7 times 10 to the negative third? That makes kind of sense, doesn't it?
I mean, you can use those if you want to.
Well, somebody do some calculating, is that
Let's move
correct?
on. The answer is yes, so it doesn't matter.
Okay, but if you just write yes, I'm giving you no credit. So Q is equal to 3.75 times 10 to the negative 30. It's not very helpful that we have these really small molarities either. 5.7 times 10 to the negative third, quantity cubed. Q is equal to, this will take me a minute, 5.32 times 10 to the negative 10th. Now I know K is equal to 1 times 10 to the negative 10th. So when I draw my number line, which is bigger, Q or K?
Q.
So Q is here, K is here. Excuse me. So the equilibrium to, the concentration to reach equilibrium would have to shift to the left, which would mean that we would have more solid formed, so it will precipitate. And, you know, don't try to do a 50-50 in this, because it's not going to make you happy.
Wait,
So yes, it does precipitate. I just don't want to play anymore.